Okay, we are back and learning about fast Fourier transform. This is the original paper of Mr. Fourier. An algorithm for machine calculation of complex Fourier series. So as you can see, this is Tukey and Young. So, and I told you one of the applications is where you have a radar signal processing. In radar signal processing, what you do is that you transmit a high powered cosine and okay, so the antenna sends a very high power signal, transmitted pulse. It hits the target and then it comes back to the receiver. Okay, so this is the way a radar works. So there is a transmitter, and antenna basically it can switch that you transmit and the receiver is off, and then you are silent and then you are receiving. Okay, so you transmit, the signal goes, hit the target, and the delay of the time at which you receive that pulse back will help you to calculate the range. And so you calculate the range, and this is how you do the target detection and ranging. So another way that what you are transmitting is this is the transmitted signal, it hits the target, and a very weak signal which has an echo in it, with a Doppler frequency in it. It's an echo signal, comes back and you receive in the receiver part. And the radar, as I mentioned earlier, that all the time you are doing FFT. So you are actually calculating FFTs. So this is a typical radar receiver. And perhaps there is a course in radars as well, and you learn this. But primarily it's a carrier, which is a cosine generator, and then you have a pulse generator. So a cosine generator, you basically mix it with a pulse. And actually it should be here that you are mixing it with a pulse. And this is a power amplifier. So you amplify, put a lot of power in it, and then you throw it in the air. And then this is a circulator which turns off the transmitter side and open the receiver side. So the signal comes here to the receiver, and you take out the carrier from the cosine. So now your left is only with the Doppler. So once you plot this, so this is how what you see in the frequency domain. If they are cluttered, like there is a hill or a building, so you receive a very strong signal back. So you see the strong signal back, and that's why they try to put a radar on a hill so that it does not encounter any static target, because wasting a lot of power. Or you basically try not to throw any power once it basically pointing towards a building or a hill. So you got to do radar planning so that you save this. If you are not doing that, still you need not to worry about this, because it's going to be a zero Doppler frequency, and this is the FFT. But if there is a target which is moving, so what you get is at some Doppler FD, you get a return. So this is a return which you're going to see, and this will help you to find out the speed of the target. Okay? The target return will help you to find out speed of the target. And so very heavy amount of computation that you're doing in radar signal processing. So this is again another application which is OFDM. And as I mentioned, the OFDM also, all it does is that the OFDM modulation is nothing but doing the inverse FFT. OFDM modulation is doing inverse FFT. And how it does that? Because if you remember, inverse FFT formula is this. So, and these are, again, you will learn this in digital communication course, that these are the information which we intend to transmit. Every piece of information is considered as the FFT of a signal, and you multiply it with an exponential, which is a carrier. So you can have n pieces of information sent at one time, because you add all these signals together and then you transmit it. At the receiver you take FFT to get that information back. So this is the technique which is used in even 5G is kind of OFDM, but 5G also uses this. But the wireless LAN uses this. IEEE 802.11a and G uses this, and then there are many other standards: digital audio broadcast, digital video broadcast, audio video broadcasting. So the DSL modem uses this, and even the SDR we are developing in CARE, we are using OFDM modulation. Let me not discuss the second problem, which is, we have discussed it, like you got to take care of the multiple reflections and which are part of this. But this is interesting, that once you are using OFDM, so this is one of the exponentials. If you plot the real of the exponential, so this is how its Fourier transform will look like. This is the frequency of the carrier, and these are called OFDM because every carrier is orthogonal to the other, because this is the peak of one carrier, a zero of the other carrier will pass through the peak. And if you plot them in the frequency, n of these carriers, so this is how they are going to look like. This OFDM is orthogonal frequency division multiple access technology, and this is the inverse FFT formula that you use, multiplied with a windowed, because you have this, and usually this is a pulse shaping filter, will shape the pulse of the signal that you are transmitting. But this is what the OFDM is, and OFDM is one of the techniques which is used in many receivers. And then the frequency is also very important, and I though requested Dr. Ali as well that we should take it to one of the frequency allocation fab site, which basically continuously monitoring the spectrum. And I told you the importance of the spectrum, that spectrum is very important, not only in Pakistan but in United States as well, because this is the most expensive resource in the universe is the spectrum. And very little part of the spectrum, we sell it for millions of dollars, like $500 billion, or actually $1 billion Pakistan can make by just licensing the spectrum, which is a very scarce resource, because you cannot create, if you have given a frequency slot to somebody, you cannot just give it to somebody else. And so spectrum is in the same region, a very scarce resource. And for analyzing, all the time you're taking FFT. You have, there is an equipment which what it does is, in the sky, it is looking in the sky, and all the time taking FFTs to show you which part of the spectrum is occupied. And if there is a part of the spectrum where you don't see that there should be a signal and somebody is transmitting, immediately you figure out that this is an illegal transmission. And for the legal transmission as well, you need to check that they are not entering in the spectrum of other people's spectrum. So usually this is, you see the spectrum, there are holes, and now there are techniques where you can fill these holes, and there may be dynamic holes, like people are not using part of the spectrum. For example, in a cellular communication, if one part is not being used, then it can be used by other people. And so this is some of the applications of the Fourier transform. But now let me just review what I did earlier on paper, that it was Cooley Tukey who invented this algorithm in 1965. okay, and Cooley 2 key. And in 1967 they demonstrated that top of the line IBM machine 794 would calculate an 8-point DFT in 30 minutes, and where they showed that they can do the same in only few seconds, as I told you earlier, that they basically demonstrated doing the same in matter of 5 seconds. So sorry, this has gone down for some reason. So only in 5 seconds. So this is the beauty of the amplitude in DFT is the magnitude of the frequency content. Amplitude is the magnitude of the frequency content, okay? So it's just the amplitude of the frequency content and nothing else. Not the number of samples of a signal. The DC value does, because in DC value it basically adds all the samples together, but it is simply the magnitude of the particular frequency. So this is the beauty of FFT, like 30 minutes were reduced into 5 seconds, okay? And we know that I talked about the convolution, that the convolution otherwise requires m into n multiplications. So m into n multiplications if you are doing direct convolution. But I have told you, like if you are using DFT, so you got to take 3 DFTs or FFTs, first of x, then of h, then an inverse. So totally there are 3 into this. The DC value does it, add value all the samples. Yes, the DC value adds all the samples together. So the DC value's amplitude is basically, as we know the DC is, just if you sum all the samples together, it may be 0, because if you have a sinusoid, its DC value will be 0. So not necessarily it will have a bigger amplitude. It depends at how much DC offset you have in the signal. So the DC value would tell you that. So we have covered this as well. Okay, now this is what I basically did on the piece of paper that you have. This is the formula, and basically this is exponential minus j x of n exponential minus j 2 pi n k over n, which is also represented by w of n, okay? And then we split it into 2 parts, n even and n odd, okay? Even we can write n as 2r, and for odd we can write n as 2r plus 1, okay? So that will change the summation, and this is the important summation that we have seen this as. So this is the summation, which is now changed. For the even, you have a 2r here and n2rk, and for odd you have 2r plus 1 wn 2r plus 1k. So this 2 we can bring down here, but we need to open this to bring the 2 down here, and once you open this, one w factor will be an extra that we can take outside the summation, and that results into twiddle factor. So we have seen this, okay, and I have given you this example where you have like 8 points FFT, you put even indices here, odd indices here. The even indices are 0, 2, 4, 6, and odd indices are 1, 3, 5, 7, okay? And then so you have r, put 0, 1, 2, 3, it generates indices 0, 2, 4, 6, and you put r again 0, 1, 2, 3, it generates indices 1, 3, 5, 7. So this formula and this formula split the FFT into 4 point FFTs or DFTs with this twiddle factor. So we have gone through this whole thing. So I'm just showing you this again because it's really very important for you to understand how the FFT algorithm works. And now you can see this, that x0 you can calculate by combining g0 h0, x1 you combine g1 h1, but once you calculate x4 you need not to have g4 and h4 because they are periodic. So you use g0 h0, you use g1 h1, you use g3 h3, and this is the lower part is the saving you get by splitting it into 2 parts, okay? So this is again the same thing is done here, just showing you the formula. So this is the formula. Now r is equal to 0 and by 2 minus 1. This 2 will get down here, which you see here. And similarly, you get this also n by 2, and you get a factor which is a twiddle factor, which will basically then appears as a twiddle factor. So you see this n by 2 coming here and n by 2 coming here. So this is a n by 2 point, and this is an n by 2 point, and this is a twiddle factor. So you get the saving. So Cooley-Tukey algorithm, by splitting n square is 64 multiplication, and having 2 4 point is 2 4 square, and then 8 twiddle factor 40. From 64 you come down to 40. Okay, this is the gain you have if you use Cooley-Tukey algorithm, and you have only done this splitting once. So now we have seen this, your first sample here, the second sample here, sample here, sample here, sample here, sample here. So 0 1 2 3 4 5 6 7, very simple. So you have 0 2 4 6, these are the 4 points. You take n by 2 point DFT, you get Z0 G1 G2 G3, and here x1 x3 x5 f7, and you get h0 h1 h2 h3. Okay, so you get this n by 2 point, n by 2 point. Now you combine these are the butterflies. Okay, now they are nicely drawn, so I thought that to show you, because I have also done some work, but perhaps though it is more colorful, but still it's better drawn like this. Okay, you see that a butterfly, so you see a butterfly like this. So this is a butterfly. So like these, you have n by 2 butterflies. And then we said you primarily bit reverse tracing. I told you that how the bit reverse tracing works, and by adding one on the other side and then taking carry on this side, so it generates all the indices. Very interesting. So now we need to understand that if you have a 64 or 16 point DFT, what you have to do is first you split it into 2 8 8 point, then 8 point into 2 4 4 4 4, and every 4 point into 2 2 2 2 2 2 2 2. Okay, so the DFT is split into 2 2 2 2 points DFTs, and your samples are like x0 x4 x6 x8 x1 x5 x, so the indices will be like these. So two points. So you take a 2 point DFT, 2 point DFT, combine them together, you get a 4 point DFT. Combine 2 4 point DFTs together, you get an 8 point DFT. Combine 2 8 point DFTs together, you get a 16 point DFT. And if you have two 16 point DFTs together, you get a 32 point DFT. 32.2, 32 point, you get to 64 point DFTs. So no matter how big your algorithm, how big your data is, you make sure it is power of 2. If it is not power of 2, because adding zeros will not really hurt your signal. So it's better that you add zeros and enough zeros to make it power of 2. So once you have a power of 2 number of samples, and remember, if you have only 7 points, the 8 point you can just put as a 0. And 0 will not hurt you, okay? It will not hurt the frequency spectrum of your signal. Pending zeros will not hurt you. So it is in DFT, FFT algorithm requires you to have your signal length equal to power of 2. Whatever is the closest power of 2, you need to make it a power of 2 so that you can do the splits. Okay, so this is the end of the day. You are only calculating a 2 point DFT. A 2 point DFT, and we have seen this. A 2 point DFT is simple. A 2 point DFT where n runs 0 from 1, and you will realize that it is nothing but you are adding 2 samples together and you are subtracting 2 samples together. So that's all it is, adding and subtracting. So all you are doing in FFT is, after splitting your samples, okay, you add 2 and you subtract 2, and that's all. This is all you are doing to compute DFT, and then you only have to combine 2 to 4, 4 to 8, 8 to 16, 16 to 32. But end of the day, what you are doing is you are only adding and subtracting, right, to calculate a 2 point DFT. And from this, then you have, so this is what I also drew. Remember, you have 0, then 4, then 2, then 6, then 1, then 5, then 3, and 7. Once you are splitting, because once you split 0, 1, 2, 3, 4, 5. Then again you split these, and I have actually drawn this, and you have seen it. And here is a better, is a little better picture that shows you a figure that shows you a 8-point DFT, where you have these two added, and though it says 0n 4n, but it will turn out to be 1, it will turn out to be -1 -1. And remember, I told you that total factors, instead of n by 2 or 4 you can have the same total factors, and you just scale it accordingly so that you don't have to recompute these factors. So you add, you do 2 2 2 2, then you combine these two together, so you get these 4 points, then you combine these. Every stage would have n by 2 butterflies. Remember, these are 1 2 3 4 butterflies. Very regular, interesting structure that has helped people to come up with interesting algorithms, not only in software but hardware. Even today you will find people doing their PhDs in finding out architecture. I was just searching on Google Scholar that people are still developing or innovating in finding interesting architecture to compute FFTs, because FFT is so critical for modern day communication and radars, and and other, even machine learning, pattern recognitions. So it has many applications. So computing FFT faster is good, and so people have been trying and devising these algorithms where you can compute faster these FFTs. So you see this, and we have already seen this. Okay, so what it does is that now because you have n by 2 stages, okay, and how many n by 2 butterflies and how many stages, it depends upon n, log base 2 of n. So log base 2 of n are the stages. For 8 you have 3, because 8 is 2 raised to the power 3, so you have 3 stages. If you have 16 you will have 4 stages. So the amount of computation are reduced to n log base 2n, okay, because log base 2n are these stages, and n by 2 are the butterflies, and you have the amount of multiplications are reduced to this, n log base 2n instead of n square. And what do you gain? That if you have a 1k point DFT, it would require you to do 2 raised to the power 20, which is 10 raised to the power 6 multiplication. Whereas if you use FFT, you only need to have 10 raised to the power 4 multiplication, means 100 orders of magnitude. Instead of computing one DFT, you can compute it 100 times. So you can just imagine, and if it is bigger size, the gain is more, because it's an exponentially, you have reduced the complexity. So amazing algorithm, and the amount of savings are just amazing. And this is, but once you sit down and try to develop your own algorithm, which is kind of recurrent and general, like it should work on 8 point, it should work on 16 or 32 or 64 or 8k point. So really you need to be very smart in order to write an algorithm which works for any value of n, which is a power of 2. Okay, I will not get into this, but this is, you can see these slides, that how you do the splitting, and we have seen it. Then you have combining them together to get the values, combining them together to get the values, and you have these butterflies, and this talks about the algorithm, which I would not really worry about. That you have stage 1, then you have stage 2, then you have stage 3, and the amount of computation you are doing and saving doing these butterfly, then these butterfly, then these butterflies. But end of the day, what you're doing is you have only the butterfly. So if you just focus on the butterfly, and that's what most of the people would do, then you can have interesting algorithm and hardware to actually do the FFT implementation. So but never ever you do the this. So this we have already seen. And bit reverse addressing, I have already told you about bit reverse addressing, that how you generate the bit reverse addressing. Now what people have done, once Kuli Tuki developed this algorithm, people have been trying to find out interesting ways of doing this, the first attempt was made where they thought that why not to change, not to split the signal into even and odds. Rather, first n by 2 points you give it to first TFT, and the second n by 2 you give it to the other. Okay, so they are not now splitting it into even and odd indices. So this is the first attempt people did that, because they were worried about generating those indices. They said, oh my god, it's a crazy way of generating indices. They don't want to do that. They simply want to split it into first half going to first summation, and then second half going to the second summation. And they realized by doing it, what they ended up was these. So this is the original, and once they did that, they came into the other order. Okay, so they tried to fix this side, and if you go through the derivation, these indices are then in the decimation order. So this algorithm is called decimation in frequency. So you cannot really get rid of the odd way of addressing. If you have tried getting away here, you will end up solving it here. Okay, so then it means that, but if you are calculating the convolution, you don't mind, because your x is in this order and g is in this order, so you have the same, you multiply, and then inverse once you get them in the straight order. So where there it can really help, but otherwise you have to deal with this. So then people thought that why not to try keeping this and this same. Okay, and they could actually able to figure out an algorithm where both are same. But then what happened? That now you don't have a regular structure of the butterflies, you see. So these are not the regular structure. So the beauty of the FFT algorithm, that will distort if you try to force linear indexing in the input and linear indexing in the output. Okay, so then again people are not happy, and once they try to bring the structure of the butterflies almost same, again you have problem with the indices. So people since then have been trying to figure out a way, but every time the simplest decimation in time Cooley-Tukey algorithm is perhaps the most optimal, though it depends on the application and the way you are looking to solve this problem. You may have a different type of butterflies, but end of the day it's better that you just use decimation in time FFT algorithm. So we have covered this. So this is our last topic. I don't know if perhaps we may cover more. It depends upon Dr. Ali what he wants me to cover, but to me we just covered our last lecture. और ये मैंने आपके लिए एक शेर लिखा मीर तकी मीर का कि अब तो जाते हैं मैं कदे से मीर, फिर मिलेंगे अगर खुदा लाया, but after solving this quiz. Okay, simple quiz. Find circular convolution of 4-point circular convolution of xn is a minus 1 to b h of n is c minus 2 f5. So you need to find 4-point circular convolution of these two signals. I think you can do this in 3 minutes, 5 minutes. Let's do it in 5 minutes. 7 minutes. Okay, 7 minutes. Okay. So best of luck in your quiz. Hopefully we'll see you next week, and we'll see what we can discuss then.